The next process is to take the minerals that we have and then put them into to reduce them. Now, the metalysis FFC process is very I'd like to talk about the complementary nature of self-replication technology and new emerging technology that could complement quite nicely interstellar propulsion technology that's of interest to people in this conference. Many of you may be familiar with the self-replicating probe, or the von Neumann probe as it's sometimes known, as a concept in which a single probe could be launched by a civilization, and then that probe could then proceed to replicate itself using the raw materials in other stellar systems to essentially colonize the entire galaxy in a relatively short space of time, astronomically speaking. This is something that I think is a very powerful technology and has all kinds of ramifications and implications to a civilization such as our own. So, the self-replication technology aspects, I'll be concentrating on that because this is something that my group have been working on for a few years and potentially could be applied as a payload to an interstellar vehicle. We begin with a concept developed by John von Neumann, the great American mathematician, who devised the self-replication process as requiring something known as a universal constructor. A universal constructor is essentially a machine which, given the appropriate resources, can build any other type of machine given the appropriate instructions, and including itself, essentially a self-replicator. So the self-replication is essentially a subset of the universal constructor concept. Now, the universal constructor comprises four major components. The first component, I would like to talk about the complementary nature of self-replication technology and new emerging technology that could complement quite nicely interstellar propulsion technology that's of interest to people in this conference. Many of you may be familiar with the self-replicating probe, or the von Neumann probe as it's sometimes known, as a concept in which a single probe could be launched by a civilization, and then that probe could then proceed to replicate itself using the raw materials in other stellar systems to essentially colonize the entire galaxy in a relatively short space of time, astronomically speaking. This is something that I think is a very powerful technology and has all kinds of ramifications and implications to a civilization such as our own. So, the self-replication technology aspects, I'll be concentrating on that because this is something that my group have been working on for a few years and potentially could be applied as a payload to an interstellar vehicle. We begin with a concept developed by John von Neumann, the great American mathematician, who devised the self-replication process as requiring something known as a universal constructor. A universal constructor is essentially a machine which, given the appropriate resources, can build any other type of machine given the appropriate instructions, and including itself, essentially a self-replicator. So the self-replication is essentially a subset of the universal constructor concept. Now, the universal constructor comprises four major components. The first component is component A, or rather sort of like system A, comprising a set of kinematic machines. We'll go on to discuss some of these systems in a bit more detail a little bit later. The second part B, the computer hardware essentially, and the computer program of instructions, which determine what the universal constructor actually builds. Now, looking at component A, all kinematic machines are essentially specific configurations of electric motors. This is my definition, that pretty much any type of machine that you can build or develop or design is essentially a kinematic configuration of electric motors. Similarly, all computing machines are based on switches or amplifiers, and this could be relays, vacuum tubes or transistors. We should be focusing on vacuum tubes as our concept for building a universal computing machine. Now, the most important constraint for a self-replicating machine is closure. What we should be focusing on is material closure. And this, if you can imagine, every device, any component of a device, has a portfolio of materials and processes and manufacturing machines required for its manufacture, both for its mining and its manufacturing. So it's important to control, to close the loop, as it were, through two procedures. The first is to restrict the raw materials inventory to minimize the amount of mining. And this will give us our demand-ite list that we'll look at a little bit later. And secondly, restrict the number of chemical processes that we need to employ to minimize the complexity of the chemical processing stage. And we should be also looking at this a little bit later. In particular, we'll be looking at using salt as a source of reagents, and secondly, the metalysis FFC electrolytic process, which is an extremely powerful technique that we'll look at in a few minutes. The second part is to restrict the parts inventory we require to minimize the manufacturing and assembly processes we need to implement. And of course, this is where 3D printing or additive manufacturing can excel. The final two parts of closure, energy closure, we won't really look into too much, other than to suggest that we want to exploit abundant sources of energy, which essentially means solar energy or stellar energy, with maximum efficiency. And we want to build an industrial ecology which minimizes waste. Obviously, waste is basically consumes energy. Processing waste consumes energy, which we don't really want to do. And finally, information closure, again, which we won't really talk about here, requires some degree of information compression. As a proviso, however, we need to employ error detection and correction methods to prevent evolution from occurring in a self-replicating machine. So this goes against the information compression requirement, but this is something we won't be addressing here. So here we have our minimal demand-ite. If you see on the table, you'll notice on the left-hand side there I've listed the material functionalities required to build a general robotic spacecraft. And on the right-hand side are essentially lunar material analogs to actually achieve this. I'll just mention here that most of the work that we've been doing in developing our self-replicating machine concept has been focused on the moon. Obviously that's of great interest at the moment, but certainly it can be adapted quite readily to exploiting asteroid material, for example. So just to take a quick look at a couple of entries here. If you look at the electrical conduction part, obviously nickel and aluminium can be used for electrical conduction in place of copper. Copper is very rare on the moon. Further down we see active electronics. I've focused on vacuum tubes primarily because vacuum tubes are relatively simple in construction, unlike solid-state electronics, which require a whole suite of reagents and very complex and difficult manufacturing processes to build. Oh, I'll also mention of various kinds. Resistance wire is the simplest type of sensor. Essentially, a potentiometer is basically a resistance wire for measuring displacement. Quartz is a piezoelectric material which can measure pressure and force. and selenium is a p-type semiconductor which can be used, which is actually photosensitive, can be used as a photosensitive component for cameras. So looking at the moon, again, we assume that there can be certain types of similarities to the moon compared to whatever asteroids we might find in the interstellar environment. The moon's regolith is impregnated with volatiles, which can be released by heating to about 700 degrees centigrade, which releases the vast majority of volatiles. In particular, what we're interested in is not so much maybe the hydrogen and the helium, but essentially the carbon compounds and also the nitrogen compounds. Most of the materials, most of the gases that we get here are actually very well separated in terms of their condensation temperatures, which enable us to use should enable us to use fractional distillation to extract them. And again, in particular, my focus here is in the carbon compounds, because they are the most scarce as far as the moon is concerned. Many of you will be familiar with the concept of reducing ilmenite with hydrogen. Everybody and his dog has been working on this for the past quite a few years, 1,000 degrees, and this essentially, the interest has always been in generating oxygen for astronauts using lunar material, using this approach. My interest is actually more in the iron and perhaps the titanium as well. Now, if we can actually marry iron with a whole host of different other metals, such as what are called tunico metals, tungsten, nickel, cobalt, and basically these materials can actually be derived from nickel iron meteorites. Now, there are plenty of nickel iron meteorite sources on the moon from impact craters. These can be extracted using the Mond process, or otherwise known as the Carbonate process, which I won't go into too much right now. But once we can ally iron with these various other types of metals, we can actually create a whole suite of alloys. Wrought iron, tool steel, electrical steel, ferrite, cobalt, and permalloy, which provide us a huge range of functionality. As you can see here, we're starting to populate our table, our demand-like table. Now, instead of, rather than looking at the moon, we can actually imagine that we could apply some of these processes are relatively complex, but if we can imagine actually on asteroidal materials, some of this might actually be significantly easier. If we take an A-type asteroid as an example, 50% metal, 50% stony, actually the metals are already in the free state, so they would actually be much simpler to extract. The C-type asteroids also provide a plentiful source of carbon, which wouldn't require us to husband the resources from the volatiles quite so much. And of course the hydrogen materials and water and so on we can get from comet material. This is the lunar industrial ecology, which can be adapted to asteroids. I've already mentioned the ilmenite just a moment ago. Here on the second section, you'll see nickel iron meteorites. This is the application of carbonyl or the Mond process to extract pure metals of nickel, of iron, nickel, cobalt, and actually selenium as well, a little bit further down, which I mentioned earlier, and also tungsten. I'll skip down to olivine, through olivine to look at anorthite. Anorthite is a very common mineral on the moon, and this can be processed quite readily through two different processes to extract essentially alumina. Now, on this slide, I've emboldened several materials. These basically are mineral oxides. The importance of that is these can be input into the FFC, the metalysis FFC process a little bit later, which will be the next slide. So here, looking at anorthite, we can extract calcium oxide and alumina. Alumina itself this also can be processed to yield, in particular here, KNO3, which is actually which is actually a catalyst that we need skipping further up, back up to the top, to extract selenium from its natural state. So this lunar industrial ecology actually wastes very little. All the waste is non-toxic. It's typically clays and so on, and there's very, very little waste through this system. So the next process is to take the minerals that we have and then put them into to reduce them. Now the metalysis FFC process is a very powerful technique, essentially a universal chemical process. It takes a calcium fluoride electrolyte. It operates in the solid state. There's no melting. It has low temperature operation, about 900 to 950 degrees C. Oxygen is evolved at the anode, and the product yielded is greater than 99% metal alloy sponge. Now this sponge can also be powdered for 3D printing, and this has in fact been demonstrated that the solid state cathode on the left, the picture on the left of rutile, powdered rutile, is then reduced into titanium powder, and this has been subsequently immediately injected into a selective laser sintering system to create some various test parts. Now the metalysis process is applicable to all metal oxides, so it can also be used to reduce iron oxides, aluminium oxides, and various other types of oxides. It yields a very, very high purity metallurgically material. One slight problem with the technique is that the anode is constructed from graphite. Now this reacts with the oxygen evolved at the anode to yield carbon monoxide and carbon dioxide. However, this can be recycled through the Sabatier process quite readily. So I'd like to talk about, this is kind of segued into the 3D printing side of things. I believe that 3D printing is a universal construction mechanism. The starting point for this is the RepRap 3D printer, which you see on the right, which can print many of its own plastic parts. In particular, the white parts that you see there were actually printed by its daddy. So this is a step towards self-replication. If we would want to go to full self-replication, there are certain things we need to do. We need to 3D print, for example, the metal parts, and of course there are techniques for doing that, such as selective laser sintering, as we saw a few moments ago. Electron beam additive manufacturing is another technique. We also need to do with joinery. In the RepRap 3D printer, this is mostly nuts and bolts, but we can replace this with cement and adhesive. What we're focused on is what I'd call the most difficult parts to 3D print, and that's the electric motor drives, the electronics, and the computer hardware software, and that's what we'll be focusing on. Full self-replication will also require some kind of ability to perform self-assembly. We'll also briefly mention that, and also requires its ability to power itself and manufacturing its power systems, which we won't really talk about here. Now, my argument is that if we can 3D print electric motors and its electronics, essentially computers, then all else follows from this. And the key step is to be able to 3D print these particular types of components. And in fact, we've been working on for the past few years, attempting to 3D print a DC electric motor. This gives you an idea of, this is one that we 3D printed. There is various different types of, we've focused on the armature initially, the rotor, and this is, here you'll see running here is a prototype 3D printed electric motor, which did just to demonstrate that. We actually applied this same a device to added a 3D printed gearing system just to demonstrate the ability to perform a very simple, basic flat pack self-assembly process, just basically essentially just moving these two panels which are jointed together. Obviously that's fairly cumbersome. You see the motor is actually external to the system, as are the gears. In an ideal world, we would like to try and shrink those to a smaller size to ensure that they're actually at the hinges of the panel rather than outside. We have in fact been attempting to do this, to shrink the size of the 3D printed motor. This was enabled through Oak Ridge National Laboratory in the US, supplying us with a permanent stator magnet, a 3D printed permanent stator magnet, to enable us to shrink the size of our motor. Now, in the middle picture, you'll see on the left-hand side our 3D printed electric motor. On the right-hand side is a commercially available non-3D printed electric motor. They are comparable in size. I would add, however, that we have not yet achieved printing of the coils. So this motor here that you see is entirely 3D printed apart from the actual coils themselves and wiring. We have been attempting to tackle the wiring part. We've tried with various techniques, which I won't go into too much. We've tried photolithography, we've tried basic extrusion of sort of like copper paste, but none of them have worked. But the one which we found does appear to work is a variation on laminated object manufacturing, which is basically using a copper sheet, an adhesive copper sheet, and then basically milling it, and then, as you can see here, removing some of the copper, excess copper, to yield essentially copper traceless on our rotor. And we applied this to a pancake motor, as you see on the bottom right here. Hello? Apologies. So here we see on the bottom right, this is the pancake motor operating with our variation on our laminated object manufactured coils. We put everything together, in fact, into a fully 3D printed electric motor. Here you'll see the components on the left-hand side of the diagram. Particularly, you see the stator and the rotor, including the motor shaft and the bearings. Everything was 3D printed, and you'll see this is what we have here. We believe that this is the first time that a fully 3D printed electric motor has been demonstrated. So nothing here was manufactured using any other technique. It's basically variations of 3D printing. Laminated object manufacturing and various other processes. One of the problems we have is that we've obviously been 3D printing the components of our motor and then assembling by hand. The next stage would be to attempt to try and address some of this limitation by creating a 3D printer which can deal with multiple materials. This, of course, is the holy grail of 3D printing. There are various multi-material 3D printers around, but usually they're fairly primitive. They don't deal with metals and plastics and ceramics together. However, what we've been doing is we've been looking at using Fresnel lenses as a source of thermal power to melt aluminium alloy. This introduces the concept of actually using solar energy as a kind of 3D printing source, thermal source. We have actually deposited molten aluminium wire onto silicone plastic insulation. Now, the aluminium in the atmosphere, but we wanted to simulate aluminium alloy in a vacuum and enable us to melt it directly. The silicone can tolerate 350 degrees C. You can actually add certain additives to actually increase that temperature, but we have nevertheless demonstrated that we can deposit metal directly onto plastic without harming it. Now, the 3D printer we're developing, so I'll just got a couple of videos here. We are developing our own in-house 3D printer, as you see on the bottom right-hand side there. The motors have already been installed, they've been tested. We need to do some certain tweaks. There's a lot of shaking, rattling, and rolling going on there. But the next stage will be, once we've corrected that aspect, the next stage will be to add the printing heads onto the 3D printer. We're going to be adding two extrusion heads. One is actually a fibre optic head, which is to perform the metal melting, and the second one is a silicone extrusion head. We already have this, and we're currently integrating that at the moment. Phase 2 of this will be to add a third milling head to allow us to mill at the same time once we've 3D printed to provide, surface finishing in an integrated machine. And then finally, we will obviously need to add a wrist to provide some kind of assembly capability within the 3D printer. Moving on to the electronics, I mentioned earlier that we're interested in, we've discarded the idea of actually attempting to manufacture transistors in a lunar environment. So we focused on vacuum tubes. Vacuum tubes are relatively simple in construction. They require all the materials that we require: Kovar, tungsten, calcium oxide, nickel, and silica glass are all we require to manufacture or to 3D print a vacuum tube. We have not yet successfully 3D printed a vacuum tube, but it's something we're working on at the moment. So moving on from that, we wanted to demonstrate the efficacy of our approach. Now, one of the problems with vacuum tubes is that if we use a traditional von Neumann architecture of a CPU, the size of the computer would be the size of a house. To obviate against that, we've decided to use neural architectures, which potentially can be shrunk to much smaller sizes. And in effect, what we're doing, we're implementing a direct model of the original Turing machine concept, where the input tape is essentially some kind of magnetic core memory, and this has the same components as a motor, essentially. The output tape are the analog neural net circuits, which I'll talk about in a moment. And the read-write head is actually the 3D printer itself. So the 3D printer becomes part of the computational architecture of this particular approach. Now, we've been using modified Yamashita Nakaruma hardware neurons, essentially analog neurons, and we have successfully demonstrated that with just two neurons, we've managed to control a very simple desktop rover to implement obstacle avoidance. And so this is just using two hardware neurons, no other computer control involved. Beyond that, we've also been looking at something that was a bit of a surprise to me. We started looking at seeing if we can implement learning systems, learning algorithms in circuit form. And in fact, we've managed to do that. The two pictures on the bottom left and bottom right, bottom middle rather, show essentially a multi-layered perceptual neural circuit with a backpropagation learning circuit, which we've successfully used to implement learning. Now, the learning was very simple. It was simply to get the rover to stop. We trained it to stop. But the significance of this was that we could actually implement a backpropagation algorithm in a circuit. Actually, these neural net circuits could be etched onto a kind of sail. So going back to the self-replicating probe concept, looking at the propulsion side, we'll assume a kind of like a modular approach to scale. Obviously, when we're talking about scales for interstellar propulsion, we're talking about essentially global scales. But again, self-replication provides us the ability to do this. If we talk about modules, we can build many, many modules in parallel, exploiting the self-replication capability. Now, I've avoided exotic materials and speculative technologies and assumed that we're going to focus on beamed energy propulsion of some kind. Now, the free electron laser is essentially based on the vacuum tube and motor components, so it actually fits in with our overarching architecture of trying to minimize the types of components that we want to build. The FEL works on using relativistic electrons, which are accelerated through Wigler magnets, alternating poles, to generate coherent radiation. And these can be tuned from X-rays to microwaves. If we look at, let's say, the forward light cell concept as a 1,000-kilometer diameter Fresnel lens, again, we've been looking at Fresnel lenses earlier, but obviously on a much smaller scale. But essentially, if you can imagine expanding this through a modular approach, that there's no reason why exploiting self-replication technology, we cannot build these types of global scale types of structures. The light sail itself also could potentially, we could replace the Mylar Kapton core with silicone, and the aluminium reflector, of course, we've already shown that we potentially can extract aluminium from local resources. Nitinol, from ilmenite we can actually get a source of titanium, which introduces the possibility of using nitinol as a shape membrane alloy for tensioning wires. And in fact, one of my students looked at this a few years ago for controlling solar cells. So in conclusion, we are currently developing self-replication technology. We've got a long way to go, obviously, but we're on, I would argue that given the appropriate levels of funding, self-replication technology may well be ready before interstellar propulsion technology. We can exploit the self-replication technology, which is characterized by exponential growth in population in productive capacity. We can exploit this to build these large interstellar type vehicles, or at least the propulsion side of interstellar vehicles, reasonably cheaply. Now, the self-replicating probe itself, or the von Neumann probe, offers the most economic approach to interstellar exploration. So if we actually implement a self-replicator as a payload to an interstellar spacecraft, it basically requires minimal capital investment, which potentially the self-replicating probe can colonize the entire galaxy in just 24 generations within 1 million years. Now, this offers the possibility of a rapid transition from a Kardashev Type 1 civilization, which is what we are now, to a Type 3 civilization in a very short timescale. It suggests that the period spent in Type 2 is actually a transition to Type 3. Given that there is no evidence of any extraterrestrial intelligent life having visited Earth using self-replication technology, it does appear we do have the first mover advantage in our galaxy, and this is actually a potential solution for the paradox. It does suggest that we are the first.